Let me begin.
We start recording.
Yes, recording is fine.
Okay, so we're very happy to have Chitraang here today to tell us something about normalization of instantons in minimal string theory. Okay, it's all yours now.
Thank you very much for the invitation. I will be talking about some sort of recent work with my awesome collaborators, Dan Stefan Enicheko and Raghu Mahajan in Stanford, and Ashok Sen at ICTS. So this is work that we published a little while ago, but towards the end, I will make some comments on things we're doing at the moment, where we're extending these results to minimal superstring theories as well. So the motivation is to start from the closed string worldsheet partition function, which is a statistical sum over the closed string worldsheets, where we have no operators inserted. So this is the standard object that you would see in your sort of first string theory course. And we usually start by considering just the perturbative piece, which is given by this z0 here. So it's an exponential of the sphere, which is this gs to the -2 term, plus the torus, plus the 2 torus. And that's the standard object that we sort of know and love in string theory. But non-perturbatively, the worldsheet can develop holes, and you also need to sum over open string worldsheets. And that is what is being captured by these other terms that I sort of denote by z1 plus ... So I can re-express this as a logarithm. Log of z is log of z naught, so the exponential goes away, and I just get the sphere plus the torus plus the 2 torus and all the perturbative guys over there. And then I end up with these non-perturbative contributions, which have been appropriately normalized for my purposes. So it's z1 by z0. And these guys typically take the form n times e to the minus t up to order g string corrections, where t is something that scales like 1 over g string, and it's the tension or the action of the instanton, depending on whether you're using matrix model or string theory terminology. So the very modest goal for today would be to compute this curly and explicitly, both in the minimal string theory and also in its dual matrix integral, and to match those computations. I will be doing this in the simplest possible case today, and I will be doing the computation explicitly. So please feel free to stop me at any point and ask me any questions. The goal for this is to be sort of mostly pedagogical. I will also generalize to other cases, but those would be in passing. So the goal is to just work with the simplest model here. So any questions before I get started? Okay, if not, I will start first on the matrix integral side. The simplest kind of minimal string theories are labeled by these 2, p models, and these typically happen to be dual to a 1 matrix integral in the double scaling limit. So here M is that 1 matrix, it's a n by n permission matrix. I divide by the volume of un, that's a normalization factor, and then there is some potential term that sits as e to the minus n over t times trace over v. V is this potential. It's typically a polynomial whose degree depends on p. So these are the typical duals to the 2, p minimal string theory. These were given to us a long time ago, maybe in the late 90s. And there's a second class of minimal string theories where the first label could be some p prime, which is bigger than 2. So it could be 3, 4, 5, anything like that. And this happens to be dual to a 2 matrix integral, where you sort of have the similar measure factors for the 2 matrices. And the potential is a little bit more complicated. So there's a v1 of m1 kind of potential term that's a polynomial that depends on p prime. There's a v2 of m2 term that's a polynomial with degree that depends on p. And then there's also a coupling term m1, m2. I will be alluding to some results for these p prime, p minimal string theories. But the goal for today would be to stick with the 2, p minimal string theories. But in our paper, we do work with these p prime, p models and actually derive some novel results using some 2 matrix integral techniques. So the first thing that you typically do to evaluate these matrix integrals is you change the variables into the eigenvalues. So your matrix M becomes some unitary times a diagonal of eigenvalues times U dagger. and you integrate out the unitaries. After doing that, you're left with just an integral over the eigenvalues that I denote by x1 through xn. There's this factor delta x squared. This is the standard van der Monde determinant, which is written here. It's the Jacobian that would come from the change of variables. Another interesting thing about this van der Monde is that if I set xi equal to xj for any I and j, I get a 0. So this guy really doesn't want the eigenvalues to sit on top of each other. So this is what causes the eigenvalues to repel from each other. And that's something that sort of counterbalances the attractive force that the potential wants to apply. So there's that term. And then, of course, there's the potential that all the eigenvalues see individually. So once I have this representation, the next thing to do is to talk about some statistical quantities. But before that, let me sort of specialize to an even simpler case, which is the quartic potential. So my potential is just has two terms. It has a quadratic term with a positive coefficient, and it has a quartic term with a negative coefficient. So the potential looks something like the sketch I have shown on the right. This simple matrix model, in its double scaling limit, which I will explain later, is going to be dual to the simplest bosonic string theory model, which is the 2,3 minimal string theory. You could be worried about convergence issues just because the potential sort of runs off to negative infinity. I will only be interested in perturbations around the saddle point, where all of my eigenvalues sort of fill a droplet around the minima at x equals 0. So I will only be moving eigenvalues away from the droplet, so the solutions don't look like most of the eigenvalues have run off to negative infinity. I'm not going to be interested in those kinds of solutions. Okay, so let me now define these statistical quantities. The first quantity that people like to talk about is called the density of states. It's basically a weighted average of where the eigenvalues are sitting. So it's just a sort of density distribution for the eigenvalues. That's what I'm going to denote by rho of x. Is normalized so that the integral of rho is going to be 1. So that's why I have this additional 1 over n factor. The other interesting quantity that people like to talk about statistically is called the resolvent. And it's defined again with the 1 over n normalization as the trace of 1 over x minus m. So those are the two interesting statistical quantities. And once you have these quantities, you do some algebra and you can write down the saddle point equation. The saddle point equation happens to be v prime of x minus 2t times the real part of this resolvent will be 0 on the cut. So the cut is the place where the density of states is supported. I will choose the cut to be between minus b and b on the real line. So the saddle point equation has to be satisfied on the cut, which is between minus b and b. I can repackage these two terms, v prime x minus 2t omega naught x, as the derivative of the effective potential. So the effective potential includes effects both from v of x, which is the true potential, and also some sort of this eigenvalue repulsion from all the other eigenvalues that is being captured by omega naught. Okay, so that is the saddle point equation recaptured in terms of the effective potential, and I can integrate this quantity out, and I can uplift the logarithms which have an absolute value to be a holomorphic sort of effective potential, which is what I've written in the second line. So the holomorphic effective potential is simply v of x minus whatever the eigenvalue repulsion piece is giving me. So it's simply the integral of the resolvent. So when I'm going to look for solutions, I'm going to make sure that the derivative of the effective potential, its real part vanishes on the cut. Any questions about this?
All good so far.
Excellent. Okay, so the one-cut solution looks like the following. So the first thing I have is the resolvent in this case. So the first two terms, as you can see, come from v prime of x. And the second term over there is sort of the additional piece that comes from this v effective prime derivative. So if you look at the second piece and plug in any value of x between minus b and b, the square root becomes the square root of an imaginary quantity. which means that the real part of omega naught minus d prime up to some factors of 2t becomes 0 because the thing that you have is purely imaginary. So this ansatz indeed satisfies my saddle point equation. From here, I can quickly sort of compute the density of eigenvalues. As expected, it is supported only between minus b to b, which is denoted by this Heaviside theta function. It has some other details. Okay, but in the ansatz, I've introduced 3 unknown parameters. These are a2, a0, and b. And to have a full solution, I will have to determine for you the values of these parameters. To do that, what I'm going to do is I'm going to require, if you go back to this slide and send x to be large, the trace just becomes a trace of 1 over x, which is 1 over x times n. So omega naught in the large x limit just becomes 1 over x. That is a condition that omega naught always has to satisfy in the large x limit. So I'm going to require that, and that will allow me to fix the constants. So if I take omega naught and I send x to be large, what I need is that the cubic term needs to vanish. That gives me one equation, which sets a2 to be minus g4. The linear term also needs to vanish. That for me will set the value of a naught. And then the third thing is that the coefficient of the 1 over x term has to be 1. That gives me the third equation that fixes my constant. One more interesting thing to note once I have the solution is that if I set G4 to be 0, so I have a purely quadratic potential, that tells me that A2 vanishes, and my solution for the density just looks like square root of b squared minus x squared. That is the standard Wigner semicircle distribution. So I do recover that Wigner semicircle in the appropriate limit. So that is what we call the one-cut solution. It's called one cut because the eigenvalues sit on this single cut between minus b and. Okay, so that captures the perturbative physics. We want to include non-perturbative corrections that come from instantons. To do that, what we do is we lift one of these eigenvalues from this droplet at x equals 0, and we put it at other points that satisfy the equation of motion. So if you recall, the equation of motion was that the real part of v effective prime needs to vanish. This happens to have another solution that is outside the cut, where the sort of leading polynomial in front vanishes. So a2x squared plus a0 still have a 0, which I will denote as x star. And if I can place an eigenvalue there because it satisfies my equations of motion. So that is what the eigenvalue instanton corresponds to. It corresponds to picking an eigenvalue from the cut and placing it at this extrema of v effective. Okay, so that's the standard eigenvalue instanton picture in the matrix model. The next thing I want to do is I want to talk about this double scaling limit, because that's the limit in which I will get my duality with the minimal string theory. So notice that the third equation that I wrote for you when I was solving for these unknown parameters is quadratic in b squared. This equation will have no real solutions for b if I take t to be too large. So if I take t to be bigger than g2 squared over 12 g4, this equation posits no real solutions for b. Zooming in towards this no real solution limit is precisely what defines the double scaling limit. So to dive a bit deeper into this, what happens is that if you consider the planar free energy as a function of G4, it has a singularity as I zoom in towards this value of G4. The reason for the singularity is that I have the planar diagrams, and typically they tend to be suppressed the bigger and bigger those diagrams get. But the suppression goes away as I tune to this value of G4. So higher and higher planar diagrams are no longer suppressed. That lack of suppression leads to this singularity, and that is the zooming in that gives me a double scaling limit. Okay, so that's the simple answer in this case. More generally, there could be multiple double scaling limits, And we need to choose the one that correctly gives me the leading order density of eigenvalues. This is a prescription given to us by Moore, Seiberg, and Staudacher. So if you have multiple double scaling limits, that's not the case here. You will have to choose the one that matches the correct density of eigenvalues. This is what the density of eigenvalues looks like. So it's some sinh of p times some arc sinh, where I've redefined some variables. So the one thing I was doing towards double scaling is take t to a particular value, but I'm doing a few other things. I am zooming in on the endpoint here, which is denoted by sort of this x being minus b plus epsilon e. Epsilon is small, so x is very close to minus b. That's the other thing that's happening here. And then e to the s naught has to be finite. That's going to become my new genus counting parameter. So if epsilon is small, n has to be big. So I'm doing a couple of things. I am taking n to be large. I'm sending t to this particular value, and I'm zooming in around x equals minus b. Those are the three things I will do simultaneously to get my double scaling limit. So that's just a reiteration of that. N to infinity, epsilon to 0, and I'm fixing e to the s naught. This e to the s naught will now scale as 1 over g string, and it becomes the new genus counting parameter. So it is suggestively called e to the s naught because we started working on this post the Saj Shankar Stanford story of JT gravity as a matrix integral. So this terminology also sort of makes contact with the e to the s naught in the JT gravity literature. Okay, so with the double scaling limit out of the way, I can give for you the explicit computation of the one eigenvalue instanton. So with double scaling, I started with the original value. I changed to these coordinates. The extrema of V effective is located at this particular E star, which for arbitrary 2, p models has the form minus 2k sine squared pi over p. In this case, I just choose p equals 3 because that's the case I'm working with. I just get minus 3 kappa over 2. Here, kappa is some energy scale that I need to define, but it eventually goes away. Okay, so that's the extrema. The next thing I need to give for you is I need to do a one loop determinant around this extrema. So I will be doing that Gaussian integral. The issue, if I naively do that Gaussian integral, is that at this extrema, instead of having a maximum, I have a minimum. So the contour is all wrong if I try to do the contour integral along the real line. So I will have to change contours to the steepest descent contour. That's the contour I'm sketching in blue for you. That's the contour I will be integrating on. Because of doing my integral along that contour, I pick up this extra factor of I over here. So that's one interesting thing that happens is I pick up this extra factor of I. The other term, this 2 pi over the second derivative of the effective prime, is the standard sort of Gaussian integral. And then this 8 pi minus E star is some other sort of bookkeeping factors that come from defining the normalizations properly. Okay, so I have this answer. I plug in my values for V effective prime and E star and all of those things. I end up with this very simple looking result where the normalization is the tension to the minus half times I over square root of 120 pi. This is an exact numerical result. This is the result I would like to match with the dual string theory picture. So any questions before I move to the string theory computation? Okay. So one last comment. I was talking about sort of 2, p models here. More generally, for these p prime, p models, the extrema are labeled by 2 integer indices m and n. In those cases, the result looks sort of similar. Here is the exact result if you're interested. So n, m is the normalization, p is the analogous tension, and then the rest of it is sort of the exact numerical quantity. So if I give you the values of n, m, p, and p prime, this is always going to be some precise numerical value that needs to match the string theory computation. The other thing is these Different instantons, of course, will have different values of effective potential at their extrema, so they will have different tensions. And in the second line, I've displayed for you the ratios of these tensions. One thing I'm doing here very carefully is that I'm deleting away all references to G-string. The reason for that is you have some sort of freedom as to how you define G-string. And we've noticed that the best quantities to work with in practice are the quantities where you've sort of gotten rid of any of those notions of G-string. So both in this ratio of tensions and this n times t to the half, my G-string factors between the various quantities have precisely canceled out. And those are the exact quantities I would like to match with the string theory. Okay, so that's single eigenvalue instantons. We can do better. In fact, we did do better. We can also do the evaluation for multi-eigenvalue instantons. So this is sort of the full result that we were able to get in our second paper, including the results for these two matrix models. So in this case, what I'm doing is I'm placing L1 eigenvalues at one extrema x1 star, and placing L2 eigenvalues at some other extrema x2 star, and so on and so forth. And I'm computing the same sort of normalization factor. So the first term here, as you can see, is simply the sum of the actions for the various eigenvalues that I have placed. The other two terms are a little bit non-trivial, but I'll try to explain them in passing. The last term is a little bit simpler to understand. It is something that scales as L alpha times L beta. So it is the Vandermonde between L alpha eigenvalues placed at x1 star and L2 eigenvalues placed at x2 star. That Vandermonde will get scaled to the power L1 times L2. So this C alpha beta is that Vandermonde plus some other bookkeeping pieces. That's the third term. The second term is really sort of the ugly looking complicated term. What you need to be careful about now is if I rigidly placed all the eigenvalues as x1 star, so if I place two of them together at that point, I will actually get 0 from the Vandermonde. So I cannot really do that. What I need to do is I need to sort of place them in the vicinity of that extrema. I need to do a quadratic approximation. And once I sort of do a quadratic approximation, I need to evaluate the matrix integral exactly. Without doing that, I'm going to get 0. If I do that exact evaluation of that matrix integral, I'm going to get something that looks like b alpha to the L alpha squared. This is the generalization of n alpha times some numerical factor, which is this Barnes G function divided by 2 pi to some power. So those are the three different pieces I get for the multi-eigenvalue instantons. Any questions?
All good so far.
Okay. So that sort of concludes for me my analysis of the matrix model side. Let me now proceed towards the string theory computation. So I'm going to be doing this on the worksheet. My worksheet theory has 3 ingredients. The first ingredient is the standard Liouville CFT that you might have seen. This is the action for the Liouville CFT. Square root G is the metric. Phi is the dilaton field. Q is some parameter I'm going to explain in a minute. Rg is the Ricci scalar coming from this metric. And then you have this last term, which is the cosmological constant term. Okay, so here B, which is a real number, happens to be a parameter. Q depends on B as B plus 1 over B. And in terms of B or Q, the central charge for this Liouville theory is given by 1 plus 6Q squared. This Q is always bigger than or equal to 2. So CL is going to always be bigger than or equal to 25. So that is the Liouville CFT piece. The second ingredient is the P prime comma P minimal model. That's where the terminology comes from. So this is basically a Virasoro CFT. This Virasoro CFT is generically non-unitary. And it has a finite number of primaries. And this will serve as sort of the matter sector in the worksheet theory. The central charge for this minimal model is given by this expression here in terms of P and P prime. The second term, as you can see, is negative, so the central charge is always less than 1. In the specific case of the 2, 3 that we are working with, the central charge is exactly 0, which means that the matter sector is empty. So it's an even nicer theory that we will actually be working with, but in general, you can work with the arbitrary p param, p minimum models. The last piece that you, of course, need to include are the BC ghosts. The BC ghosts have the standard central charge -26. Now I will require the condition that the total central charge of the Liouville CFT plus the minimal model plus the BC ghost vanishes. That gives me the condition that the B parameter of the Liouville CFT is related to the P prime and P parameters in the minimal model, and I will choose the value of B that is less than 1. The JT limit in this language is taken by sending P prime to 2, letting P run to infinity, which sends B to 0. So that's that's the reason for this convention, that we want the JT limit to sit not at B goes to infinity, but as B goes to 0, which is why I choose B equals P prime over P inside the square root. Okay, so that are the ingredients that I have in my theory. Let me now go forward and talk about what the worldsheet sort of boundary conditions look like. So on the Liouville CFT side, I can have 2 types of boundary conditions. The first type are the FZZT boundary conditions. These are typically labeled by a parameter called mu b, which is the cosmological constant. I will not be interested in these boundary conditions, but these lead to some interesting class of branes. The second class of boundary conditions that I will be interested in are ZZ boundary conditions. These again take the labels m, n, similar to the labels I was talking about earlier when I was referring to the extrema of the effective potential. So they take the same labels. And in fact, these ZZ branes are the things that give me my non-perturbative effects of interest. So let me define the symbols on this side. T, which happened to be the action at the extrema, will now be the tension of these ZZ branes. So it roughly scales like the amplitude of the empty disk. So it has that 1 over G string factor as we expect. So that's the first quantity. Sorry. Okay. And then if I now look at the expression for Z1 over Z0, I will sort of get an empty brane. But then once I allow for these boundary conditions, I can have single cylinders or multiple cylinders ending on these boundary conditions. That's what I've sort of graphically or visually depicted for you in this cartoonish picture. So I can isolate the boundary condition piece, which is this e to the disk or e to the minus t piece. And then I capture all the cylinders together. Because of the appropriate symmetry factors that I have between those various cylinders, I end up with an exponential of the cylinder. So that gives me the identification that this curly n is the exponential of the cylinder. So the goal now will be to compute the cylinder, or more precisely, the exponential of the cylinder. Now, if you recall from the previous analysis, we saw that n scales like t to the minus half. So n scales like 1 over square root G string, which tells me that the cylinder has to have a logarithmic G string based correction. That seems very strange because once I start evaluating the cylinder, initially there will be no explicit references to the G string. So that's actually quite a strange thing, and that's what's the most puzzling bit of this picture, is how does the cylinder get that logarithmic G string dependence? The puzzle will become a little bit more clear once I write down the integral expression for the cylinder, but I just want you to be mindful of the fact that it's really surprising at this level that the cylinder has this logarithmic dependence. Okay, so let me now set up the computation for the cylinder, or the annulus partition function. I'm going to be doing this in the open string channel. So T for me is going to be the open string time. I can define the Q for it, which is e to the minus 2 pi t. The annulus partition function for the Liouville CFT, where I place the simplest sort of 1-1 boundary condition on both ends. So these are those ZZ labels I was talking to you about. I place those 1-1 boundary conditions on both ends. This is what the Liouville annulus partition function looks like. eta is the standard dedekind eta function. Since the matter sector was empty, you can write it in two different ways. You have this sort of generic expression for the matter annulus partition function, but also we know that the matter sector is empty. So if you exactly evaluate this, you'll just get 1. So matter sector is trivial. And then the ghosts give you some other dedekind eta function squared kind of contribution. So the full thing that we want to compute is the normalization exponential of the cylinder. I will have to integrate over the modulus, which is the open string time. So that's the integral over dt. The 2t is a symmetry factor. The 2 comes from the fact that both the boundaries for the cylinder are the same. So I have that exchange symmetry. And the t comes from the symmetry that I can sort of rotate the cylinder and choose the t equals 0 wherever I like. That I need to multiply by the f of t, which is the product of the 3 different annulus partition functions that I gave for you. So it's the Liouville times the matter times the ghost. Once I assemble all of that, I get this sort of relatively simple looking integral that I need to evaluate. So I can give it to my favorite undergrad and hopefully they give me an answer. I give it to my favorite undergrad and catastrophe strikes. So what happens is that the 2t in the denominator might be scaring you a little bit, but in fact that limit, which is the UV limit, is completely regular. There are no issues because the numerator also has zeros at t equals 0. But if I look at the other limit, which is the IR, the t goes to infinity is in fact divergent. It is divergent because if I look at this f of t and expand it in the large t limit, I get e to the 2 pi t, which is exponentially divergent. I get this minus 2, which because of the 2t in the denominator gets me a logarithmic divergent. And then from then on, everything is regular. So 2 interesting things have happened. So far, this curly end has no references to G string. Very surprising because that's what's expected. The other thing that has happened is that I've gotten an IR divergence. I need to cure these things. This is an IR divergence. I'm going to use string field theory. Those words make people very uncomfortable, but this is a very low powered version. So hopefully you stick with me. But before I go there, any questions about what's happened so far?
Good so far. Actually, here's a quick question. What's an intuition behind that divergence as t goes to infinity? How should I think about that?
Excellent question. So that's basically coming from either, so this is an IR divergence. You have tachyons and you have zero modes. This is the divergence coming from those long-lived IR modes. So it's the e to the 2 pi t is a tachyonic divergence. The minus 2 is a zero mode divergence. So that's the intuition. I'm going to explicitly give you the modes in a little while.
Okay.
Any other questions? Thank you for the question.
I think we're good.
Okay. So answering your question even more in a more detailed way, here are precisely the tachyonic and zero mode states. So let me sort of unpackage what the table is doing for you. L0 is the sort of L0 eigenvalues. So the first 2 rows are my tachyonic states. The next 4 rows are my zero modes. NG is the ghost number. The third term is telling you whether this field lives in the Siegel gauge or not. So the first, third, and fifth lines, which are shaded in light blue, are the Siegel gauge modes. The first line is the Siegel gauge tachyon, which was giving to me that e to the 2 pi t. It's bosonic, so it comes with a plus sign. The third line, which is the 0, and then the C1, C minus 1 acting on 0 are the zero modes. They are in Siegel gauge. They are fermionic, so that's the origin of the minus 2.
So a quick dumb question. Remind me, is Siegel gauge, the Siegel gauge states are basically the physical states. States that aren't satisfying the Siegel gauge, I should basically think of as unphysical. I'm really rusty on string field theory.
That is correct. That is correct. So naively, that's what you would say. We will pick up some beef with Siegel gauge towards the end, but naively, that's what happens. So initially, at least, the Siegel gauge states are the physical states. Those are the ones you're dealing with. So there are 3 Siegel gauge states. There's precisely sort of those 3 things that are giving me the divergence here.
Okay.
Yeah. So initially, they are the physical states. So I've told you what their Grassmann parity is, which tells me the sign. And then the last thing is I'm going to give them some labels to just do the bookkeeping. So this Siegel gauge tachyon, I'm going to call phi1. The Siegel gauge zero modes, I'm going to call P1 and Q1. And then there's this other state I've labeled as psi. That's the one that's going to be interesting for us, and that's the one that's going to solve our problems. Okay, so what do I do next? My f of t, as I said, I can represent this as a sum over the bosons and fermions with their appropriate sort of L0 eigenvalues. So the f of t in general takes this representation, which is a sum over bosons minus a sum over the fermions, where HB and HF hat are the L0 eigenvalues. This is all in Siegel gauge. In these terms, I can now very easily evaluate n without worrying about divergences. So just treat everything as sort of regular. The integrals all work out. What I get is a product over the fermions in the numerator divided by the bosons in the denominator. That's sort of the standard story when you do these integrals. The fermions actually happen to be paired. So there are always two fermions which have the same L0 eigenvalue. You saw that in the zero mode story, but that's always true. So I can break it down as the square roots only go and live in the bosonic sector. So that's the second simplification I do. And then this ratio of numerator and denominator, I write down as a bosonic Gaussian integral and then a fermionic integral over two labels. So the first piece is the bosonic piece. If I do all those integrals, I'll get all of those factors of 1 over square root HB. And then the second term, if I do those Grassmann integrals, so PF and QF are Grassmann odd, I'm going to get the factors of HF hat that I need. And that sort of gives you why I had labeled those as phi1, P1, and Q1, because those were the ones that are sort of the associated fields. So this is the representation I'm going to be working with. And I now need to cure two things for you. I first need to tell you what to do with the phi1 mode, which has HB1 equals -1. And then I need to tell you what I do with my P1 and Q1 modes, which have H hat 1 equals 0. So let me start with the phi1 mode. And in some sense, I sort of do the simplest thing that I need to do, which is the phi1 has e to the phi1 squared over 2. This Gaussian integral diverges if I integrate it along the real line. So I again rotate my contour to be along the imaginary line. This contour change is exactly identical to the contour change I did in the matrix model side. So if I choose the other direction of the contours there, I have to choose the other direction here. So that if you were worried that there was an ambiguity, whether it was a plus I or a minus I have exactly the same ambiguity here. So there is a one-to-one correspondence between the contours in the matrix model and the contours in these phi field integrals. So that gives me that sort of factor of I that you were worried about. Where am I going to get that from? This real integral. This is where I'm going to get it from. I'm going to do it, get it from changing the contour. Great. This was easy. The hard part is what's happening to the P1s and Q1s. Ashok Sen tells us that in these cases, the Siegel gauge breaks down. I cannot operate in Siegel gauge anymore. What I need to do is I need to sort of zone back. I need to consider all the modes properly. I need to use a more physical gauge, which in this case happens to be the gauge where I only keep the fields of ghost number 1. So going back, P1 and Q1 are bad fields. I don't keep them. I keep the field of ghost number 1, which is phi. That's sort of the classical field. I'm allowed to keep phi1 because that's also a ghost number 1 field. So no surprises there. So that's what I'm doing. I'm changing from P1, Q1 to phi. So in the first line, or the numerator, what's happened is that I have a d phi, and then e to the minus phi squared. This minus phi squared is the open string field theory action that comes from an explicit calculation. In the denominator, because I've sort of lifted the gauge freedom, I need to divide by the volume of the gauge group. The theta parameter there is my gauge parameter, so I'm dividing by the integral of d theta, which is just going to be 2 pi, which is going to be the periodicity of theta, which is my gauge group volume. So what I'm doing is going out of Siegel gauge and doing an explicit computation where I've not chosen any particular gauge. And I need to divide by the volume of the gauge group to account for that fact. Okay, So that's the technical part. What is happening here physically? So just for some intuition, if instead of d instantons, we were working with p branes, what would have happened is that the 0 would have changed to a k state, which is e to the I kx acting on the 0. And I would additionally get an integral over these k's. I would get a dp plus 1k. In that case, the Faddeev-Popov prescription would give me a k squared. There might be divergences, but I can always regulate those using an I epsilon. So in ordinary quantum, ordinary sort of cases of DP branes, there's no issue. Maybe there is some I epsilon prescription that does everything for me. What's happening here is I have a d instanton, so my k is rigidly fixed to 0. I no longer have the luxury of an I epsilon prescription that can fix things for me. That is why Siegel gauge is breaking down, is because k is fixed to 0 rigidly here. Okay, so that's some physical intuition about what is happening. I cannot have k running. I don't have momentum running anymore in my loops, which is why k is 0, and there's no epsilon here. So what happens is what used to be your local U1 that gave you sort of phase rotations on the DP brane has become a rigid U1. And this rigid U1 has a parameter theta tilde, which exactly has the 2 pi periodicity. And my gauge group theta is related to theta tilde by this rescaling over GO, which is the coefficient of the cubic term in open string field theory. So theta tilde has sort of periodicity 2 pi, which tells me that my theta is going to have a periodicity of 2 pi over GO. That is precisely the integral I need for my denominator. The numerator simply integrates using standard Gaussian integrals to a square root pi. So I end up with a square root pi divided by 2 pi over GO. Standard tachyon condensation arguments tell me that this GO is related to the tension, and I get a precise value in terms of the tension. So this is how the tension enters the story. It enters through these 0 modes which had gone rogue. So this is the other piece of the puzzle. The 0 modes have gone rogue. I go into sort of this physical gauge. I fix everything properly there. I get a GO factor from the volume of the gauge group, which is related to the tension. Okay. So now I have all of the pieces assembled for you. The normalization is I, coming from the bosonic tachyon. I have this second factor coming from the fermionic 0 modes. And then the third factor is all the other pieces, which are perfectly finite, so I didn't have to worry about them. So those I can just integrate naively, and I get this pi over square root 15. I multiply these guys together, I end up with the precise answer that I had in the matrix model case. Any questions?
All good so far.
Excellent. Let me also talk about the generalization next. Again, what I'm interested in is I have L1 ZZ branes of type 1, I have L2 ZZ branes of type 2, yada, yada, yada. I want to evaluate Z of L1, L2, dot, 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 normalized by Z0. The first term is just sort of the sums of the tensions of these various ZZ branes. So that makes a lot of sense. The last term is the cylinders connecting L1 ZZ branes of type 1 to L2 ZZ branes of type 2. So the factor L1 times L2 comes from the fact that on the one end, I could have chosen any one of those L1 guys. On the other end, I could have chosen any one of the L2 guys. So C alpha beta is the cylinder between the alpha ZZ brane and the beta ZZ brane, and then that L alpha L beta scaling shows up quite naturally. In this case, the fact that B alpha scales to L alpha squared is also natural, because now B alpha is just a cylinder between two ZZ branes of the same type. And because I have L alpha varieties of those, for either end, I could have chosen any one of them. So that's the L alpha squared in some sense. The other things are just some, again, bookkeeping factors that I'm not going to go into the details of. But that's how this formula is basically represented in the various pieces. So B alpha is the cylinder where the two endpoints are the same. C alpha beta is the cylinder where the two endpoints are different. The second one happens to be perfectly regular, so you don't have to use any string field theory to regulate that. It's a perfectly regular thing that you can evaluate using standard techniques. Okay, so let me now conclude. It might be a bit early, but I'll make some comments about what we're doing in the future. So we've been able to match the instanton correction across the duality between the minimal string theory and matrix integrals. This is not just for the simple 2,3 case that I showed you today, but also for general multi-instantons in these P prime, P models with sort of all the gory details of the two matrix integrals and all the gory details of the string field theory. We get that exact match. The numerical coefficients match exactly. The thing we would like to do in the future is to extend these results to minimal superstring theory. And why this is interesting is because now these things have a phase transition, which is an analog of the Gross-Witten-Murdia phase transition. We were able to make some progress on the matrix model side. An interesting feature that we noticed on the matrix model side is that naively, the tension has the wrong sign. So the tension which you expect to be positive, the eigenvalues, if you move there, the effective potential happens to be negative. So instead of getting things that are exponentially suppressed, you get things that are exponentially enhanced. That's a really bad thing. So the resolution there is that instead of moving real eigenvalues, you sort of move these anti-eigenvalues to that point. So these are some sort of holes for the electrons that the eigenvalues. You need to move these holes there. And this means that on the matrix model side, if you have these anti-eigenvalues, the conjecture would be that you would have some sort of anti-branes, anti-ZZ branes on the string theory side. People have been very sloppy at computing the tensions because they usually fix the sign by hand. So a question we would like to answer are there objects of this class that exist on the string theory side if we can find a way to fix the tension in a more robust manner. So people would usually choose the plus sign because the sign was something most calculations are ambiguous to. You typically compute t squared, which is the easier computation. So that's one reason why we want to study this. And then there's also this phase transition, which is triggered by instantons. So the instantons on the one side of the phase transition reorganize, trigger the phase transition, and then turn into a different class of instantons. So understanding what happens to these ZZ branes across the phase transition is a question that we would like to answer. And this is work in progress with Vivek Chakrabarti, a PhD student at UPenn, and then my long-term collaborators, Dan Stefan and Raghu. And with that, I would like to thank you for your attention.
Thank you. That was a very nice talk.
Thank you.
Questions?
Oh, what did I do wrong? Is this? Yeah, questions.
So yeah, so maybe let me ask one question. So how about this computation or this dual between this minimal string and the matrix model thing can tell us something about the holography maybe? Is there any I don't know, like some target space holography I can think of from this computation from this minimal string example?
So the standard story that people told, this was the Sarshankar Stanford story, is if you can take a JT limit here, which is dual to this double scaled SYK. And a question that one would like to ask is what happens to that similar story in minimal superstrings? Witten and Stanford had a paper about this, and they discovered one of the phases of the super JT model. But as I said, there's a phase transition, so there's the other phase. Again, that phase is relatively unstudied. The matrix model tells you there is this other phase, but no one knows what this other phase of super JT looks like. So there might be interesting questions about what that phase is, what its holographic dual is, and so on and so forth. So all the things that we know from this JT SYK duality might have sort of interesting analogs here that still need to be studied. So that's one answer that I have.
I see. Okay, great. Thanks.
Of course, yeah.
Yeah, if there is no question, let's thank Chitraang again.
Yeah, thank you for the invitation and thanks for attention.
Thanks for speaking. It was a very nice talk.
It's a nice talk.
Thank you. All right.
It was a pleasure meeting you, and
Yeah.
until
Yeah,
James
hopefully-
Muller said hi.